Uh, So we got more electrical principles.
And you have like E5B. Where did you get that number from? So how does it,
That is E for extra,
oh, okay.
5 for sub-element 5,
Okay.
B for group B.
Okay, so element 5 on the AARL or
In the question pool, the FCC question.
in the question pool?
And that's the way they're numbered there.
Okay.
So each sub-element will have A through as many as F or G groups.
So that's good. I should have written it down for the last one. Do you happen to remember what the numbers are on the last one? Because that
It was E5A, alpha. We're doing group at a time.
oh, gotcha. Okay.
Okay, so we're going to talk about time constants and phase. Normally we refer to the RC time constant, but there's also the RL time constant that works the same way. And also what happens to the phase angle in reactive circuits, which we kind of already talked about for resonant circuits. And then a little bit about admittance and susceptance, which you probably never will use, but it's on the exam.
We'll use it once.
Yeah, you use it once.
I need to apologize to everybody real quick. I'm on to go. With my back surgery count, I can't sit here and pay any attention. I'm at catch next class. No,
Okay.
thank you. Sure. Oh,
Yeah, so yeah. Do you need help?
no, I'll make it. I might be a little slow, but I'll make it. Thanks, y'all. Sorry.
Okay.
Take care.
Here's something.
Okay. So when we have an RC circuit and you apply voltage, you start charging up the capacitor because you're storing energy in it. And you're putting those coulombs in, if you remember back in the basic stuff, where current is the amount of coulombs per second. And effectively, the capacitance is the number of coulombs that are stored in that capacitor, which equates to joules, which is actually the measure of energy. When you start charging that capacitor, essentially it looks like a short circuit, so you get a high current initially and zero voltage across it. As it charges up, okay, the current decreases and the voltage increases. And depending on the product of the resistance and the capacitance, that's called the time constant. In one time constant, it will have charged that capacitor to 63.2% of the applied voltage. After two time constants, it will do another 62.3% of the delta. And after three time constants, it'll do it again, and you'll be up to essentially 95% of the applied voltage. In theory, you would never charge it up. But in practice, after three time constants, you're essentially at the input voltage.
It's almost like a reverse half-life. Like it never gets to 100%.
Well, yeah, I mean, it's like, in the football game, you keep getting half the distance to the goal, half the distance to the goal, you never get there.
You never get to the goal, right?
So the main thing to remember is the 63.2%. And I just approximated as 5/8, which would be 62.5. So it depends, if it asks for the exact number, you got to remember 63.2, but it's basically 5/8 of the voltage. And on discharge, it's kind of the inverse. So it'd be 36.8. in both cases, after 3 time constants, either 95% charged or down to 5% charge on the discharge side. So if you plot this, I don't remember what value R I used in this circuit, but as you apply a 1 volt pulse to that, you can see how it charges up. And these lines are approximately a time constant. So after like 3 of them, you're basically charged. When you take the voltage away, the capacitor will start to discharge through that resistance, and it'll go down in that same time constant effect. The formula actually calculated is this nasty thing up here, which you don't have to know.
That's the formula for what?
For the
For that curve?
for the rise or fall
Okay,
as a function of time.
okay.
So it's T over tau, and tau is the time constant. So you got to do the e to the minus T over tau thing.
What is T in seconds?
T is in seconds. Yeah, I should have mentioned that. T is in seconds, and R would be in ohms, and C would be in farads. So you got to use your minus 10 to the minus whatever. So what's the term for the time required for a capacitor in an RC circuit to be charged to 63.2% of the applied voltage or discharged to 36.8?
E.
Using one telling us.
Yeah, I would have had to ask them.
One time constant. What's the time constant of a circuit having two 220 microfarad capacitors and two 1 mega ohm resistors all in parallel? They did this to trick you.
Yeah, I was gonna say.
Morning, Phil.
Just wanted to blow off.
Delta?
I have a delta.
Well, I got a question. Would you simply,
All right.
Yeah.
Everything just zeroes out.
Yeah,
I think.
It's like 1/220
yeah,
times 2 times 2, 2/220.
Yeah, when you put
yeah,
capacitors in parallel, what happens?
You add the,
They add, right?
yeah,
If
Okay,
you put resistors in parallel, it gets smaller, right? So you can do the nasty 1 over the reciprocal of the sum of the reciprocals, or in taking the fact that it's only 2, and they're equal, you just divide by 2. If they were different values and you had 2, you can multiply them and divide them by the sum and get the effective. The reciprocal of the sum of the reciprocals always works, but it's a pain to do. So we had a delta, several deltas. Looks like delta's the winner. Because you're basically 440 microfarads and a half a mega ohm resistor. So 0.5, if you cancel out the 10 to the 6th and 10 to the minus 6, then you're 0.5 times 220 or 440. Okay. In an AC circuit, the voltage and the current in that circuit are only in phase when it's a purely resistive circuit, or it happens to be an RLC circuit that's in resonance, because that's the only time when you got inductors and capacitors that there's no phase shift at resonance. So the current or the voltage and the current are proportional based on Ohm's law. As you increase the voltage, the current increases, and vice versa when you decrease. When you have capacitors and inductors in there, you're not talking about a resonant frequency, then you're going to get phase shift. And one of the things that they teach to remember the relationship between voltage and current for inductors and capacitors is Eli the Iceman, where Eli means E the voltage, L in an inductor leads I the current. So if you think about it, if you got an inductor and you apply a voltage, okay, you initially have the voltage, but you have zero current. So if I apply a sine wave to that inductor, the current follows as a sine wave, but shifted by 90 degrees. So that's the case where the voltage leads the current. In the case of a capacitor, that's the Iceman or ice, where the current I in a capacitor, C, leads the voltage. So in a capacitor, charging it up, the current will increase before the voltage increases.
I'm gonna have to go back and look at that slide. Very different.
Well, maybe these others will help.
Oh, pictures do you?
Pictures help. Okay. In a capacitor, okay, we apply the voltage. You see, we have initial current very high, no voltage. Okay. And as the cycle goes on, okay, the voltage rises as the current is decreasing. So that's a 90-degree phase shift. So we say this is the Iceman, okay, that the current leads the voltage. Okay. So what's the relationship between the AC current through a capacitor and the voltage across a capacitor?
You can go back again.
It's the ice. Yeah.
Okay. So the current leads the voltage by 90 degrees delta.
What's okay, in an inductor, okay, now we're back to Eli. It's kind of just the opposite. So the voltage leads the current in an inductor.
Okay. So inductor is Eli
Right.
and
With the L.
capacitor.
And ice with the C is for a capacitor. So picture is, okay, the voltage, okay, is increasing before the current. So there's a 90-degree phase shift the other way. Because in the inductor, it's like it has inertia. It's going to resist current flow initially. Whereas capacitor is just the opposite. I mean, it sucks up the current until it charges up. It's kind of like the water analogy with, filling up the tank, and it'll fill up until it gets to the equal pressure with the amount of water pressure coming in.
Mhm.
And then when you take the pressure way back down, kind of way a capacitor works,
Okay,
where the inductor is more like a flywheel. There's inertia to get it started. Once you get started, it keeps spinning until you take it away, and then it slows down. Those analogies work for basic, but. So what's the relationship between the AC current through an inductor and the voltage across an inductor?
You like.
Yeah, it's Eli.
Hey,
They're an alpha. Corey.
I'd say, well,
All right, he wins it. Eli. Okay, so if we have a simple RLC circuit. We've got a resistor. We've got to make sure. An inductor and a capacitor. So the impedance of that circuit, which we use V to represent impedance, is going to be the resistance R plus the inductive reactance, which would be plus JL, minus JX sub C for the capacitive reactance. We use the negative sign for the capacitive reactance because it's a minus 90-degree phase shift. And we plot it on the negative portion of the y-axis when we plot these. And that is a vector. Okay, so you can't just add the resistance and the reactance together. You have to add them vectorially because of the phase shift. Unfortunately, we don't have to get into all the complex mathematics, which I had to endure. And once again, these last statements are really talking about Eli the Iceman, okay, where the voltage leads the current or it lags the current. It's another way of saying it in capacitor. Instead of the current leading the voltage, you can say that the voltage lags the current. So if we plot resistance and reactance, or basically plotting impedance, because it is a vector, okay, we plot the resistance on the horizontal axis on the rectangular coordinate. We plot the reactance on the y-axis. If it's inductive, it'll be a positive. If it's capacitive, it'll be a negative. And if they're both there, then you have to look at the sum. So you would subtract the capacitive reactance from the inductive reactance and then plot the result. When you draw a line from 0 to whatever that reactance point is, that's the length of that line is the magnitude of the impedance. And if you remember the Pythagorean theorem,
A squared plus B squared equals C squared.
right? Okay, so the magnitude or the length of that vector is going to be the square root of the resistance squared plus the reactance squared. And the angle, because there's phase shift, okay, and the fact that there's resistance and reactance, it's not going to be effectively 90 degrees. You're going to have a different phase angle depending on the ratio of the reactance and resistance. So the phase angle is going to be the arctangent. And remember, the tangent is the opposite over the adjacent side of the triangle. So the angle that's equal to that tangent, okay, is going to be your phase angle. Sounds more complicated than it is.
It is.
On your calculator, that will normally be like a second function on the trig. to do the arctangent. Or sometimes it's called cotangent, or it'll be tan minus to the -1 power. So an example is, what's the phase shift between the voltage across and the current through a series RLC circuit if the capacitive reactance is 1,000 ohms? And remember, we do reactance still in ohms. The resistance is 1 kiloohm, and the inductive reactance is 500 ohms. So we add the reactances, so we'll get a -500, and we divide that by the resistance, which is the adjacent side. And then we look up what the arctangent of -0.5 is. And it should come out and say that it's -26.565 something degrees. At least it does on my calculator.
So let me try to understand, so the 500 minus 1,000, that's because the voltage is leading the,
No, it's because the inductive reactance was 500. The capacitive reactance was -1,000. So the sum of the two is 500, -500.
I got that.
okay, so again, I'm trying to wrap my head around this. Why is it minus instead of?
Because
Because you do 500 minus.
people a long time ago said that capacitive reactance was negative. Because it's a 90-degree phase shift as opposed to a positive phase shift, which is why we do it negative. And they're both imaginary, which is why they have a J in front.
Okay, the difference is 500, I just, why is it not 500, but minus 500?
Right, because we always use the minus sign for the capacity part.
Okay,
Did everybody have?
No, I'm wondering if you could go back to the drawing and maybe like say what part is,
Okay. This one?
yeah, that one right there. And so,
Okay, this line on the bottom is resistance,
okay,
so that would be 1,000 ohms. So if I had this mark, I draw this out to 1,000, wherever that was. And our effective reactance was -500. So it's actually going to be down here instead of up there. So just tend to flip it over, because the line's going to be like this,
I see.
okay? And your actual vector point's down here.
Okay. That makes sense.
And the angle is the 20 -26. And we say that the voltage is lagging the current because it's a negative. Or you can say the current is leading the voltage, however you want to say it. Oops. I gotta unpoint it. So, real one. What is the phase angle between the voltage across and the current through a series RLC circuit if capacitive reactance, we didn't do a subscript on XCC, is 500 ohms, resistance is 1 kiloohm, and the inductive reactance is 250 ohms. So it's the same problem, just different numbers. So first you have to find out what the effective reactance is by. Adding the two together.
I got 14, now I gotta wrap my head around the leading or lagging for it.
Is it positive or negative?
It's negative, so it's lagging.
Okay, I didn't get to the 14. How did you get to the 14?
So I took our calculator you have. Type the second tangent. Get that?
I got tangent, so here's.
Yeah, do the second function and to give you the.
Oh, I see,
There.
okay.
Yeah, you get it, and then the arc tangent, put parenthesis. And another parenthesis. And then put 250. Minus 500. Because your capacitance is 500 and your inductance is 250, right?
Okay,
Put a end parenthesis. Divided by 1,000. Which is your kilo. Put the other parenthesis in there. It equals.
oh.
So you get 14?
So he's got it right there.
Yeah,
Was it negative?
It's lagging.
it's negative. Okay, so negative would be the lagging.
Right.
Okay,
Capacity.
capacity.
And remember, just remember Eli the Iceman. So it's capacity. ICE. Current leads the voltage. Or voltage lags the current, whichever. Current lags the voltage doesn't fit with Eli the Iceman. Okay, everybody good on that one?
I wouldn't say good, but sure.
Well, then, there's another one. So the odds of getting one of these is getting greater.
Mm,
So we have 300 ohms capacitive reactance, 100 ohms resistance, and 100 ohms of inductive reactance. Same problem, different numbers. It's just an exercise to see if you can use your calculator.
Let's see if I can remember that first, where it goes. Okay, so. Okay, I have a tangent. Parentheses, you see parentheses, and then I realize I'm not sure how to select these to put them in.
Okay, so what?
So I'm ready to put the formula in now,
Okay,
and I
so
realize
put in the inductive reactance minus the capacitive reactance,
okay,
and divide that by the resistance. And that'll be the tangent. And you want the arctangent, which is the angle that's equal to that tangent.
okay, so the inductive resistance minus the resistance, and then what did you say?
The capacitive or the inductive reactance minus the capacitive reactance divided by the resistance.
And that's where I get tangent. No, I put divided
Yeah,
by.
that will give you the tangent. Okay, you want to find the angle that's equivalent to that tangent, which is the arctangent or tan minus one or cotangent, depending on your calculator.
Okay, so do I push tangent?
You have to do tangent and second function to get the arctangent. If you do tangent, it should give you, so what do we got? 300, so 200 over 100 or 2. So I don't know what the tangent of 2 is off the top of my head.
Okay, could I get somebody to do it on the calculator and show me?
So, let's see.
Thank you.
See, it figures out. Okay, so start by. See, there's 10 minus 1. Okay, so second 10 minus 1.
Okay,
Right, and then what are the numbers again? Can we get
300 and 100.
So open with 2 parentheses. Oops,
okay,
fix these, right? Okay, 100
and you got that, okay, from resistance,
minus 300,
okay,
and then you close one set of parentheses. So
Okay.
you still have another,
okay,
and you're gonna divide that, this response, which is, that will come to negative 200, you're gonna divide that by 100, right?
okay,
Close your second set of parentheses
okay,
and hit enter.
oh. Well, that's very clever. All
Yeah,
right,
parentheses are your friend. You really can't have too many, but
okay,
if you have not enough, you'll be in trouble.
okay,
Right.
So everybody comfortable with
So you see how what we put there, arc 10 minus
Yes.
1, same thing. And we did the exact same formula right there, just in your calculator formula.
gotcha, okay, now, so what I have is Eli is an inductor leading the current, but we're talking about capacitor,
right,
right?
which is Iceland.
Right, which means that
The current leads the voltage, or the voltage lags the current.
okay, these
So
voltage,
you can hear.
voltage line, okay, all right. Whoa, okay. Getting mad now.
Okay, today is the hardest part,
Good,
except for remembering the rules and regulations, which some people find that easy, some people don't. Okay. Oh, gee, another one.
thank you.
Boy, the odds of getting one of these is getting better and better. So we have 25 ohms capacitive reactance, 75 ohms inductive reactance, and 100 ohm resistance. So it's the same old formula, different numbers. How you doing, Amy?
Good.
Got any answers yet? Did I hear a bravo?
Yes.
Several bravos?
From
Well, let's see.
I didn't pick my numbers right, so and then I tried changing the numbers, so. I'm gonna need to hire a tutor.
Just remember, you can miss 13,
Right.
so you can really miss all of the math ones as long as you do good on everything else.
Okay, all right,
If you get the second tangent,
yeah, yeah. I did second
yeah,
tangent,
then you have to start with two parentheses, whatever L is. You take that and subtract your C
oh, okay, so I'm right
and
there,
divide the sum.
So we have 50 over 100,
so,
okay? And it's positive this time.
so L minus C, because L is,
XL minus A.
Is 75. Right, X of L. And X of C is 25. So it's a positive 50 divided by 100. So the tangent is 0.5.
okay, XL is 75, okay, so I get my numbers all,
And the arctangent of 0.5 is.
here we have, so this one.
Okay.
All right, so XL minus
XC.
XC, thank you,
And the sum of those, because there's parentheses here on those, divided by R, which is 100.
okay,
Arctangent, find the arctangent of that,
okay,
and it'll give you 27,
okay.
positive 27.
And then why am I choosing XL first? Because XL is what?
You don't have to, but you have to put the capacity reactance in as a negative number.
Oh,
So
well,
I could do capacitance first, and I could do minus 25 plus 75,
okay.
same thing.
Okay, tell me what I'm subtracting now. I'm taking,
But you're actually adding,
I'm adding.
you're adding the two reactances.
Oh.
You gotta remember the capacity reactance will always be negative. So the order doesn't matter as long as you use a negative capacity reactance.
So although it doesn't show negative there, I have to make it negative.
Right,
Okay,
because you're supposed to know that capacity reactance is negative.
I'm supposed to know that.
Yeah.
I will do that.
You do need to know that.
I will do that.
And you could write this formula, well, we didn't do the whole thing here.
So,
As the sum, though, you could add X of L plus parentheses minus whatever X of C is,
okay. I was just gonna,
because you're actually adding them.
okay, I was gonna take a picture. But I
Well,
will,
these slides are on Dropbox.
yes, I know,
Okay.
and I will go there. I'm
Okay.
definitely going there.
Okay, admittance.
Are very helpful.
Yes, yes. Have you already looked at them? You should.
I just kind of scanned through them,
Yeah.
but now he's going through
Yeah.
it, they are very.
I made a few changes since I put them up there, but nothing significant.
Yeah, I started looking and I didn't understand them, so I just stopped. So now this is
Now-
good.
The video for the previous class are on YouTube,
Mhm.
and there's not that much difference. I mean, 80% of the questions they've reworded. It's the same thing,
Right,
just
different wording.
different wording.
Okay,
And a lot of them, all they did was reword the wrong answers. So that you can't memorize the. And it was a lot of work to change the slides. Okay, admittance. Admittance is the inverse of impedance. Remember, we define impedance as the opposition to current flow. Admittance is just the opposite of it. It's the can't think of the right word other than it admits current instead of impeding it. And that's why I think why they chose the name.
It unimpedes.
Yeah. And it's the reciprocal. So it's equal to 1 over the impedance, or 1 over Z.
Admittance is equal to 1/Z.
Right. The reciprocal of impedance. And actually, it wasn't all that long ago. It used to be in MOS, MHOS, which was ohms backwards. So because it was reciprocal, and they would represent it. The omega signal, which you sometimes see as an ohm, like a horseshoe,
Yeah,
upside down, was a mode.
okay.
Sometime here in my lifetime, they decided to honor some guy Siemens, and they now use Siemens to represent the admittance and conductance and susceptance instead of ohms. They just like to confuse things. So we also have susceptance, okay, which is the kind of equivalent to reactance in the admittance formula. So for impedance, you have resistance plus reactance. In admittance, since it's the reciprocal, you've got conductance plus susceptance. So conductance is the opposite of resistance. It's how well it conducts as opposed to how well it resists. So here's how they're laid out. So resistance is, you can think of it as the reciprocal of conductance, or the conductance is the reciprocal of resistance. We don't have a question on conductance, but it's just part of the set. Reactance, we represent X, is the reciprocal of susceptance, and susceptance, which is a B. Why, I don't know B, but it's reciprocal of reactance. And impedance is the reciprocal of admittance, and admittance is reciprocal of impedance. So those are just reciprocal relationships. When we represent these in polar form, okay, we do the magnitude of the vector and the angle, just like those examples we did. So when you convert from impedance to admittance, you take the reciprocal of the impedance magnitude and change the sign of the angle. That's what these two things are trying to show. So if it's impedance, I can represent it in polar form by a vector of length z, which is the square root of the square of resistance and reactance. If I want to represent that in polar form in admittance, then I take the reciprocal of the impedance vector, the length of it, the magnitude. That's why the two vertical bars representing magnitude. And then change the sign of the phase angle.
Okay.
You don't have to know it for the test. Okay. And I think we only have one question or two. What is admittance? No math in this one.
Yay.
Minutes is the first step. Acknowledging the problem.
Okay.
Good. Admittance admits, impedance impedes. How is impedance in polar form converted to an equivalent admittance. We just talked about that,
Mhm.
that very complicated looking process, which really isn't.
Hey, okay.
Bravo.
Reciprocal magnitude.
Amy,
Yeah.
oh, come on.
Well, C and D are on the table, right? So we got A and B.
Go.
What was that?
Magnitude.
Oh, the polar form, yeah.
So we're gonna go from this to this.
So change the sign was what
Right.
threw me there for a minute. So yeah, okay. Well, the whole thing's throwing me. I mean, how much you think I'm sitting here going,
So reciprocal of magnitude and change the sign of the angle. I'm not sure where you're gonna use that,
thank you. 'Cause-
but it could show up on the exam.
Two cars heading in opposite directions, 160.
Okay, what is susceptance?
Anyways. See,
That's the made up thing.
yeah.
Very good.
Why do we have to learn it? It's made up.
Huh?
I said, if it's made up, why do we have to learn it?
Well, just because it's imaginary, it turns out that's the way we represent phase. Okay. And we use the complex math, which is why you get square root of -1 in there to show the phase shift.
I could have told you.
I wondered the same thing when I took advanced engineering mathematics, and that's all we did. Where am I going to use this? Hmm. Hello? Yeah? Yeah, they,
So this light problem. Can you give me permission to rejoin?
yeah. Let me see.
Sorry to bother you like this.
If I can find you. Oh, there you go. There you go.
Thank you so much.
Okay. Are you good? All right. All right. Did we do the last one? The imaginary part, right?
Yeah.
So what letter is commonly used to represent susceptance?
Well, so do you want me to say Bravo or do you want me to say Delta?
Well, the correct one would be Delta Bravo. That's correct. Yeah, just remember the B for susceptance because it doesn't have any connection.
Okay.
At least with impedance, there's kind of a Z sound in it.
Yeah.
What's the effect on the magnitude of a pure reactance when it's converted to susceptance?
Delta.
Remember when we did the conversion on the previous
Yes.
question? What did you do?
Made the reciprocal.
Right. Okay, so we learned about time constants. Remember the 63.2% per time constant. The time constant is the product of the resistance and the capacitance or inductance, works the same way for an RL. Um. And it's ohms times farads. And 3-time constants, you're effectively charged up to 95%. And remember Eli the Iceman. You can write that on the back of your answer sheet when you take the exam.
Oh, you can,
Oh, yeah. You put anything you want on the back of the answer sheet.
okay.
Just do not write in the booklet because some of the examiners will get very upset.
Especially with Gary.
Especially Gary. Well, all of them do, because they only have a limited number of booklets. Now, if you take it online, it's not an issue because there's no paper booklet. And you get random tests. Everyone's different.
Oh, really?
Yeah.
Hmm.
Okay, and then we learned all this nasty stuff about resistance and susceptance and conductance and how to convert in polar form. Okay?
So let me back up to something you just said. So when we take the test, I didn't realize this. So like if all of a